So I thought I'd tell you a little bit about this space probe reboot project that I was lucky enough to get pulled into. And who's actually heard about ISEE-3? Okay, a couple of you. So there was this old NASA space probe that was launched in 1978, and it was called the International Sun Explorer. It was launched as a part of constellation of 3 satellites to go out and do various observations. It had quite a wide array of scientific payload on board, and ISEE-3 itself was later put into a heliocentric orbit, but it was designed to study the interaction between the solar wind and Earth's magnetic field. Later on, it was renamed ICE, and it had a number of firsts. It was the first spacecraft to be put into this L1 Lagrange point, and it was also the first spacecraft to pass through the tail of a comet. Every other nation that had space capability was chasing down Halley, but the US wanted to be the first, so they repurposed this one temporarily to fly through this other comet and beat everyone else. And the Lagrange point is interesting because it's at this particular point between the Sun and the Earth where it can sit in a stable orbit as the two bodies, or as the Earth rotates around the Sun, and it will get dragged along there. And NASA wanted to experiment with this particular point in space, so they sent a probe out there. And there's this incredible mind-bending orbital maneuvers and trajectory that they had actually designed for this particular. Apparently, one guy at NASA was able to visualize this.
They got lost.
This in his head.
That was before graphical computing.
Yes.
So
consider that when this was launched, it didn't actually have a computer on board. It was really primitive electronics. It was just essentially shift registers and sequences. And if you think about it, that's probably what has contributed to its longevity, as you'll find out. So if you consider that it was originally launched then, it fulfilled its mission. NASA ran out of funding to complete the project, and they put it into this graveyard orbit to essentially go around the Sun. And every so often it would catch up with the Earth, and so now this is 2014, and it would do this lunar flyby. And another way of visualizing that trajectory would come by, this was actually when it was visiting that comet. This is the broader view as it actually goes around the Sun. This is relative to the fixed Sun-Earth line. And so it departed Earth in '83, and it was due to return in about 2014. So this is an interesting animation here that shows you the original trajectory of the probe. So what you have to imagine is that the Sun is out there, and the camera is following the Earth around as it orbits the Sun. So it was initially launched out there. And this is the L1 point, the Lagrange point. So they did many orbits around there. And then did some crazy maneuvers to give it some kinetic energy, do lunar flyby, and then slingshot back out. Yeah. And then it went into the orbit around the Sun. And so this is the probe itself. It's actually spin stabilized, and it has S-band transponders on it. It has a number of different thrusters configured for moving in different directions, and that scientific payload. So all these science experiments, some would measure the solar wind, plasma waves, magnetometer, and so on. Some of them failed, other ones were apparently still logged as operational. The telemetry that's sent back from the probe would obviously help the NASA boffins analyze the state of the probe. And here is an example of an old screen that's actually showing you the state of the hydrogen propulsion system and various other parameters of the onboard subsystems. So this was, I guess, a bit of inspiration for what you'll see later. By the way, if anybody's got any questions, please feel free to interrupt and ask. So the original mission had drawn to a close. Telemetry was actually disabled, so they kept the transponders active and transmitting a carrier, but nothing was modulated on there. And what was interesting is that NASA decommissioned all the ground-based equipment that they had used to communicate with the probe. So unfortunately, anybody that wanted to communicate with it after the fact just wasn't able to, because the equipment was no longer part of the deep space network. And the documentation for it had been scattered. So this new mission came about, co-led by Dennis Wingo and Keith Cowing, and the idea was to recapture the space probe because in 2008 its transponders had been picked up by some hams in Germany, and since it was coming back to the Earth and going to do the lunar flyby, there was the potential to turn it back on.
how many watts was the carrier?
I think it's 5.
Holy crap. And how far away was it when they first received it?
It was many tens of millions of kilometers. So the idea was to enable the telemetry via the thrusters, if we could get the propulsion system working here, and bring it back into orbit around the Earth. And the idea was to turn the science instruments back on and open it up to public science. And this wasn't something we were doing just on our own. There was a lot of discussion with NASA, and in the end, this space agreement was actually signed with them. So we had a lot of communication back and forth. Now, the interesting thing is that when they realized that it was returning to Earth and this mission came about, there was only a relatively short period of time to get moving, because obviously when it gets closer to the Earth, the amount of fuel required to make that trajectory correction will increase, and then eventually beyond the amount of fuel supposed to be on the probe. So this is the range of the probe relative to Earth over time, and you can see that it's coming in pretty hot there. And if you consider the delta V, I think these are old numbers, but it still illustrates the point that beyond a certain date, the delta V, which is required to make that correction, will exceed 100%. And of course, you can't use more fuel than you have on board. So then we had sort of these pretty hard deadlines for making the thing actually move. And then this was another way of illustrating it. So this was the max amount of fuel on board, and then things got pretty hairy pretty quickly. So we were hoping to sort of try to make some progress before that. So if there was to be a success case, then the probe would come in and then end up doing this sort of maneuver there and then come into orbit around the Earth. If it was to fail, then it would come through, slingshot by the moon's orbit is here around the Earth, and then just continue back out into the solar system. So to get things rolling, this is obviously quite a popular practice now, but they raised funds on the internet, in this case Rocket Hub, and quite a princely sum as well. And the problem was that the probe was out there. They managed to sort of do this techno-archaeology to find all the old NASA documentation for the probe, but the original radio communications equipment was no longer available for us to use. So we needed to create a new modem to talk to the probe, and this is where SDR comes in. So through, I guess, a bit of a fluke, they got in touch with Matt Edis, and he forwarded them on to my former colleague and I, and we got talking, and they actually ended up purchasing some usurps, and we set these up all around the place and actually used them to talk to the probe. So at the time when we were getting this rolling, the probe was approximately 15.5 million kilometers away from the Earth. Oh, there you go, 5 miles. And it has 2 S-band transponders up there for uplink and downlink, 2 antennas, there's a medium and an intermediate gain one, and what this means is that you're not dealing with your average budget. So to actually figure out where it was and to calculate Doppler shifts and so on, you can go onto NASA's JPL Horizons website and then punch in various, for example, space object IDs, I think they're called, that will actually give you, when they're visible in the sky, where they will be Doppler shifts and so on. Well, not the Doppler shift, but the velocities. And there was some preliminary sort of trajectory computations done by some people to figure out where the spacecraft would be going. And as it turned out, it was a little bit off this calculated path. So it meant that when we were trying to find it, we had to scan around the sky a little bit to try and pick the signal. So to actually aid with this, I wrote a little Python code, and it would actually read in the output of JPL Horizons, and then it would give you these sorts of real-time stats. It was just really cool watching it flick by, so it would tell you the speed that it was traveling. I mean, the insane speed, really. At one point, it was 4 kilometers a second, flying through space. Distances, this would eventually tick down and back up again. And the other interesting thing was when we were actually doing the comms, taking into account the 2-way light time. So this would be the idea that we would send something up and we'd have to be in suspense, waiting patiently until something would hopefully change on our screens. And then in addition, you would have the frequencies here, and because the Earth is rotating and the probe is moving, we have to take into account this Doppler shift. So you have the nominal values, and then we calculate, this program will give you what the actual peaks would be. And then eventually, I won't go into those details later, but all this stuff over time was sort of integrated into this big new radio sort of creation that I put together. I call it the Master Blaster. And so this would then feed in part of the front, the sort of upper layers of the application will automatically take into the Doppler shift into account, because those USEPs that we were showing you before, actually have a daughter board that can do native S-band. And so that would be sent up over the fiber optic link to the out transmitter, and that would sort of all just take care of itself. We didn't need to have an upconverter or anything like that. But to do the long distance comms, you need a big amplifier and a big dish. And so
your backyard?
We were fortunate enough to have a little bit of a trip to the Arecibo Radio Telescope in Puerto Rico. You may remember it from such movies as
James Bond,
Contact and GoldenEye. That's it. So it was pretty wild. This is the catwalk, and then the dome in here. It looks tiny, but it's actually multiple levels in here, transmitters and receiver equipment. It's crazy. And
fun.
that was fun.
So that's all suspended by a cable?
That's right, yes. So they have these towers and the entire platform is suspended. It doesn't shake from side to side. We did have an earthquake. That's another story. What's interesting is that this needs to be suspended at a particular height above the dish, so that obviously the focal point meets up at the right point. And so they actually have tie downs that come off the various points of the platform, and depending upon, there's laser altimeter, I think, to actually measure the height of the platform, and the tie downs are these massive concrete weights underneath the dish, and it actually has motors that pull the platform down to ensure that the height is at the correct point. I mean, it's an incredible setup, and it's enormous. It's 300 meters in diameter, 1,000 feet in.
What's the game?
I'll get to that. A lot. So actually, you can then go up the catwalk onto the platform, and then go down through a series of steps and ladders and things like that, and get into the dome. And this is a new thing they're working on there, setting up some ionospheric heaters to study the atmosphere. And then here, this is my friend Austin. We walk down these steps, and then we go through and have a look at the transmitters and the receivers. We had some amazing people along the way. Dana, he's the microwave guru who helped us set everything up. That's Dennis, the co-lead. Austin's the engineering brain box, like I say. And then they also have this separate way of getting up there, which was good fun. But we took a little ride down to the center of the dish because you can go underneath. And then looking up is quite a view as well. And by the way, if you're interested, I took my GoPro with me and filmed pretty much the entire thing. So if you're really keen to look more, I've published a whole bunch of videos on my YouTube account. And this is actually inside the dome now. So they have the secondary and tertiary mirrors there, essentially, that bring the photons to a particular focus. And the cool thing is that they have multiple receivers that actually sit on this rotatable floor. And when they want to select a particular receiver, they just punch in a couple of commands out the control center, and then the floor rotates that feed horn to the focus. And so you can see different experiments have different sorts of feed horns there, and they get rotated. And because they also have transmitters that end up putting out an enormous amount of power, they have these shuttles that go over the receivers because they're cryo-cooled and they're extremely sensitive and very expensive to replace. So this is back in the control center. This is my friend and former colleague, John. And you can see here the status of the platform and the weather and all sorts of other interesting bits and pieces. And they have CCTV so you can see inside the dome there. This is Austin was up there, and they were doing some I'm not quite sure what they were doing there, but they were looking at some of the experiments. And this is interesting too. You might recognize this is probably going around the room, but they make a big point about RFI there for obvious reasons. And they actually have special shielding that they add to the cables there in the ignition coil and other things in their vehicles. So this is actually what it looks like underneath the dish. So it's quite nice. And yeah, you can go down and have a look. So apart from being a receiver, they also transmit. And one of the interesting experiments they do there is S-band radar work. And they do planetary radar. Excellent. So they look at asteroids. They actually produce these incredible RF images of asteroids. So there's the again.
That'll.
At S-band. Now it's a very narrow beam, obviously, so you have, and also limited steering on the entire dish. they can move the platform, so there's the azimuth arm, and the platform itself can rotate. So you have some...
We get about 20 degrees, or how much?
20, 30, something like that.
So they can't rotate the planet?
Yes, they can, once a day.
Yeah. Well, and that meant for us, we had a particular window of time that would run up. And luckily, it fell into the maintenance period. So because it's narrow, we needed that accurate ephemeris to actually be able to lock onto it. And yeah, there was obviously the side load to get locked anyway. So this is one of their classrooms there. They use, we were hoping to use an existing setup, but it didn't quite work. Their thesis is very low, obviously, and we wanted to use this, but the frequency uplink frequency to talk to the probe was actually something outside of their setup. And they have dual 1 megawatt S-band classrooms that are power combined and then transmitted out there. At that game that I showed you before. So we needed an alternate transmitter.
Be good combined.
But nevertheless, that's what you get.
See, kid, see.
So this has actually happened.
So you don't want to fly over it?
Well, I think, I never saw this, but apparently they've sort of flown through, or they've actually come to perch inside the edge of the dome while this was active. And so I've been told, in no uncertain terms, and in some graphic detail, that what happens is they are boiled, for obvious reasons, that S-band. They fall onto the dish, and they catch fire. And the problem is that because now you have this foreign object on the dish, it will end up reflecting quite a bit of RF energy back into the dome, which you don't want, because it's bad for receivers.
Dinner.
Yeah, right. So we needed another transmitter, and so we had this custom power amplifier built by this ham in Germany, Dirk Fischer, and we had it shipped international overnight FedEx because we needed to get rolling. And it was really an interesting design because he had combined 4 UMTS inspired amplifiers, and I think it was about 450 watts out of that. And we then attached that to an existing waveguide in the Arecibo setup. And that's how we then were able to transmit the frequencies that we needed. So this is what it looks like. It's this incredible design. Has anybody seen the movie Prima? I recommend that you do. It's pretty great. But there's this box in it, and so it's very reminiscent of that. But this is the waveguide, and then they would have the amps, and these are massive heat sinks for each of the 4 amps there. And we would need to raise that, so we went down into the center of the dish, put it in here, and then hoisted it up, and then installed it up the top there. So back to that time window, we had about 2 hours and 45 minutes each day through which the space probe would pass through our visible window. And the schedule there is incredibly busy. So, as I said, luckily it fell into that maintenance period, and we could do some work there. It would be quite a busy period of setting all our equipment up because obviously we would have to vacate after that and nothing could be left behind, so we'd have to go there with our laptops and usurp and hook everything up to their patch panels, which I'll show you in a minute. And in addition, while we were there, we would constantly need to switch between transmit and receive mode, so they would need to rotate the floor and open and close the shutters and so on. So there was that to take into account too in terms of the timing. So what we did there is we had 2 of the usurps connected, and they would have the receivers running, and they would go through a couple of intermediate stages, and then down at the control center with their patch panel, we got IF out at about 260 meg that was centered at the frequency that we wanted to listen on. And what's neat is that we could choose between alternate polarizations and the downlink frequencies, because the space probe had the 2 different frequencies. So here we just got it hooked up, and this one's the network model, so I've got it plugged in via a switch into my laptop and looking for the signal on the FFT there. And this is what the IF panel, part of the IF panel actually. So I think one of the first stages comes out here, it goes into another stage, and they have all sorts of fancy filters, and it goes through more stages at the bottom. They can control the mixes with these synthesizers, and then all sorts of configurable attenuators and various other things and buffering. So part of the setup of any observation, any experiment for anybody would be going here and actually figuring out where to plug all your patch cables. So it was trial by fire, really. You had to get on that pretty quick.
What did they think of you guys coming in and sort of doing all this? Did they view it with professionalism or just leave the hacks to my
No, they were really great. And I think part of it was because it was something new. It was a little bit outside the norm what they were doing, and you know, to a degree they were happy to sort of support this new mission. It was a bit of excitement for them as well as for us.
Different.
Yeah, and they were really great about it. And this was part of the diagram that I received to figure out how the patch panel actually worked through all the stages, so you should track it through there and figure out where to look up. Now, in addition, because they do a lot of observations that are combined with receivers all around the globe for very long baseline interferometry, they have a hydrogen maser as their station reference. So these SDRs are capable of accepting in a 10 megahertz input as a frequency reference.
GPS.
Yeah, GPS is usually one thing, and then a PPS so that you get time synchronization. So in this case, we had not your average reference, and this was fed out of all sorts of house sync patch points, and we would hook these up to the receivers. So in fact, the receivers would be synced to this incredibly accurate source, and because we had two separate units, I wrote a bit of software so that when they started receiving the signal, they would actually inherit the global time, and then the recordings will be precisely timestamped down to the sample accuracy of 10 nanoseconds long like that, based on its reference. And that was neat as well. Yeah, that was neat as well because, as you said, you can have a GPS module plugged in, and then I guess an additional extra you can get these. These actually have a GPS DO in them, but in this case we weren't using a GPS, and the GPS is neat because not only does it give you the references, but it gives you the time via the media stream. And you might be able to appreciate this, but in this case we had this reference, but we had no absolute notion of time. So what I did was, they run an NTP server, and obviously your accuracy of NTP is only going to be so good, but because you're getting a 1 PPS signal, you only need it to be accurate to the second. So what happens is, when I would start the program up, it would assume that the clock on the PC is already synchronized to NTP, and as long as it's within a second, you're good. And then it waits for the next PPS tick to come in. And when that tick happens, it latches the current time plus a second, and then you're good down to the 10 nanosecond accuracy, whatever it is, of your frequency reference. So that way we could establish very precise timing over multiple radios. Now this is an example of what's known as a GNU radio flow graph. So GNU radio at the lowest level is C++, so it can run very efficiently. On top of that you have Python, because it's easily scriptable. That gives you sort of a glue layer to plug all these blocks together. And then on top of that, you have this graphical interface, and you can use the software at any level. But to do sort of quick programs and experiments, it provides you this graphical environment in GNU Radio Companion. And you can drop these blocks down and link them up like that. This describes the flow of data or samples through your flow graph. So in this case, this was actually the simple recording program that we used to run on the receivers to actually see the signal and then log it to a captured file with that very accurate timestamping. So to give you an idea, this block here represents the USERP, which is the source hooked up to the dish, and then it goes through into these ones that will capture the file to the hard disk, and then it goes through these ones and it puts it into a waterfall sync so you can see graphically what's going on, as well as an FFT sync. And then down here, this is the complete baseband version, and then down here it goes into this frequency translating FIR filter, which comes back to your question about how you deal with that large amount of bandwidth. So you can take that in, and this will actually then decimate it down to a much lower sample rate, a much smaller bandwidth, but then you can move it around in your complete band and then pick which sort of subband you want to actually capture and listen to. And those will also go out to a waterfall and an FFT sync. So what would happen then, when we initially fired everything up, this is the waterfall plot, and amazingly we have our tiny little weak carrier there being received from the space probe. And you can see because of the Doppler effect, you obviously have that diagonal line there. So it was unexpectedly quite weak, and so we probably weren't pointing directly at the space probe, because the ephemeris needs to be programmed into the Arecibo control computers, and that actually drives the movement of the platform and the focus. So we needed to do that. And the guru's there, one of the guys there is amazing, he figured out and picked everything up. So we were pretty happy to see this. And again, the amazing thing about this is that back in the day, NASA would have had these huge racks of equipment to do all this sort of stuff. We've turned up with a laptop and an SDR and plugged in, and Bob's your uncle. So the ephemeris was stale and it deviated from its predicted path, and it was in the side lobes of the dish, so it required a manual search of the sky to peek it up, and it was done by Phil there, and some of it was done semi-automatically, but in the end, we did that, and then we got a much better signal in there. And actually, people from Google Creative Labs came down and filmed the whole thing, and they made a little doco about it, which is neat if you want to follow up with that later. We were pretty happy about that. And then I took a much longer capture, and then you can, because Python's really nice and flexible, there are great toolkits for it, like NumPy and Matplotlib. So I wrote a bit of software that would go through and actually plot the entire capture, and you can see over a much longer period of time how it travels there. And then this is focused on a very narrow channel, but if you were to look at the complete baseband spectrum, I don't know if you can quite see it there, but there's this line there, which is the spectrum. So it's not diagonal because we're not zoomed in as much, just looking at the complete band.
So how much more signal did you get afterwards?
I'll show you that. So here, this is actually just zoomed in now on a normal single FFT. Just to give you an idea, this is the noise floor, and this is very, very low resolution bandwidth. So you know when you're using a spectrum analyzer, everything depends on the resolution bandwidth. If you dial it way down there and do, I think this might have been a 1,000,000 point FFT, you can resolve incredibly weak signals. And here, I was zoomed right in there, and this is all the carrier is, just above the noise in this case. But once you do the peaking, then it improved quite a bit. So this is, what's this one? I think it was half a hertz RBW. We got 45 dB. So that's significantly better than what we had before, which is great, which is what we'd hoped to get. And you can see here that I've got peak hold on, and as the signal moves due to the Doppler shift, it's causing it to move the peak hold. So this was great, and then because it was transmitting on 2 different frequencies, we had both radios running and we could see the signal there. So that was sampling that. If you actually analyze the signal further, there's this great software out there called Boardline. It's one of my favorites. It's free, but it's not open source. And it's a great tool for analyzing RF signals. You can do amazing things with it. And in this case, if you zoom in, you can actually see this additional wobble in the frequency. And this is going to be seen at extremely small RBW, huge FFT size, and this is due to the spinning of the probe. So that was quite an interesting thing. And because there is a sensor on board that should report back the spin rate,
So
you can also derive the
17 a second or something.
Yeah. And you can also derive the spin rate from this.
From the wall.
Is that because the antenna's on the outside sweeping around?
Yeah.
Oh, okay. So it's coming towards you going away, right?
And so it got a bit of widespread coverage. And this photo unexpectedly turned up on a number of different publications. And just for a bit of additional humour that you might appreciate, later on, when the Lunar Flyby was happening, we had particular journals come out from a particular publication. So if you might have picked up this in December last year.
Pages of stuff.
Only read it for the articles.
Only read the articles. There we are.
Mission out of control.
If you go back a page, you'll see something completely unrelated to that.
So that was when the mission was out of control.
So to give you an idea about the uplink, we were able to successfully get the carrier. Now we needed to send commands to the probe to wake it back up. So we had a dedicated USEP set up for transmit. It had an SPX daughter board in there so it could do the S-band natively. And it was really cool because they don't want any digital equipment to be up in the dome. They don't want anything that has a clock because that will create harmonics in the EMI. So we had the transmitter down there in the control center, and then we had this fiber link that would come out, that would take the signal out of the USEP, take the RF over fiber all the way up to the dome, go out of the equivalent on the other side, and then go into the power amplifier. And so we were setting up there, peaking the signals, making sure all the levels were right, calibrating that. And this is their incredible racks of equipment there, and we were given this little spot. But they have all sorts of other interesting equipment there to do incredibly wide bandwidth experiments. So my friend knocked up this really simple Flowgraph again that essentially implements the old NASA spec. And this was interesting too because, I'm going to get to that in a second. So we did, there were some interesting things about this, but I'll talk about that a bit later. This is the output on a Spec Hand just to make sure the signal looked okay. The interesting thing was there was so much documentation and there was so much ambiguity in it that we weren't even sure what the correct numbers were. So certain things like the phase modulation index were different values in different documentation. So we had to take that into account and be able to run with these permutations when we were on site. Because we only had the limited observation window, we didn't have a lot of time to do that.
How many hours a day would you have visibility in the right direction?
2 hours and 45 minutes. And that would slowly shift through the day as they went on. So to ensure that things would work, I also created a demodulator for the uplink. So, unfortunately, if the mistake was in the spec, then it would be replicated in both, but it was still worth checking. So this is the flow graph for that. And it's interesting because, we could test it, run the transmitter, and then run the receiver and see what it looked like, see if it matched the spec. It's phase modulated. And it's also interesting because it has an FM component that describes the digital data, whether it's 1 or 0, but then it also has an AM component that conveys the clock. So remember that there's no computer on board, it's a very, very simple bit of electronics on the space probe. So it derives the clock from the AMing in the signal that you send it. And then it's phase modulated, so it shouldn't have a particular look on the FFT, which it did. And then once you demod it at a particular point in the graph, you can see how you have the clock there, and then you have 1s and 0s. And it's self-clocking, which is pretty neat. It's a neat idea. And then you can run it through the clock recovery algorithm and give it a rating and so on, and it all looked pretty good. So at that point, we were pretty confident that hopefully at least the signal going out would be right. We didn't know whether the receiver on the spacecraft was still working. And then we also knew that the telemetry coming down was convolutionally encoded, had this incredibly long constraint length if you know anything about convolutional code. And it was this quick-looking variety that was popular around the time that the probe was designed. And if you're interested, you can check out that paper, Non-Systematic Convolutional Codes for Sequential Decoding in Space Applications by Maxime Costello. So fingers were crossed. And this is the moment where we're sending the commands out, they're being logged here. And as you might remember from the demo that I showed you at the beginning, we were running HDSDR, and I was also running it there with a B200, same setup that I demonstrated before, but consider that there's this massive dish that's outputting this enormous amount of power. Some of the RF energy is going to spill over the side, so I could just have my little receiver there, tuned to the frequency, making sure that the signal that we were sending here was actually ending up on the air.
So that's when you transmit Seeber.
Right, exactly. So this is the leak coming over there, just to make sure things are working. Because there was a point where something went wrong at some point, and we thought we were transmitting, but in fact something hadn't been connected up here. I think the PA wasn't correctly connected, and actually nothing was going on in the air. We couldn't figure out why we weren't having any success. So this is what happened. We sent out the command, and we managed to hit it at the... didn't plug it in.
No audio.
Try it one.
Do it again.
Call the president.
So we were quite happy there. Lots of celebration. So what had happened there is we could send the command to turn the telemetry back on, so that unmodulated carrier suddenly became modulated data. At this point, we weren't able to decode it yet. We still had to implement all that stuff.
When you say you weren't sure about the exact commands and the phase shift and whatever, did you try like a sort of send a few commands and then hopefully one of them works? Or?
Yeah, well, we were pretty sure that the raw bits in the commands were correct.
Yep.
And then it was more about taking into account the Doppler shift on the uplink, as well as potentially any frequency offset that the probe had experienced over time.
Yeah.
One theory might have been because we're constantly stepping through a range of frequencies to try and hit it on the mark.
Yeah.
And as it turned out, at that point, the design of the transmitter wasn't really suited for, let's say, a very consistent reception. I'll talk about that in a minute, but yeah, it was mainly sort of stepping through the frequencies, and it seemed to be very hit and miss at the beginning.
Sure, I was trying to figure it out.
But yeah, we had the capability there of changing the modulation indices and so on. And yeah, so that sort of worked out. Does that answer your question?
Sort of. I was just wondering if you had sort of had like you had about 3 or 4 educated guesses that you fired up, and then waited for the round trip to come back.
Yeah, well,
And then-
that was what we
Yeah.
actually had to do.
And then you figured out it was one of those that worked.
Yeah, well, actually, so the way we did it was because there was that long period of time. If we subtracted from that the amount it would take to rotate the
Work
transmitter
which one
receiver,
worked.
we had a certain window through which we would send a certain number of combinations up.
Yeah.
And if something worked, then we knew that something in that group had worked, and then we
Yeah.
would try them
Yeah.
individually. And the first day we actually had, I think, no success, but then the next day we did. And so you can see there now that carrier has been modulated with that. And you can see at the waterfall, if you zoom in again to that chunk of baseband, you can see the characteristic shape. What was interesting is that some of our collaborators in Germany, the guys that I believe initially discovered the signal on the way back, simulated what it should look like, and then if you overlay it, it matched up perfectly. So that was really nice to see. And we had only a carrier on B, but telemetry on A at that point. And so transponder B did not respond to commands, and because it was so far away and so on, it might have just been a marginal link. Transponder A did respond. I think we tried B, and that's why it didn't work on the first time, and we switched to A. And A seems to work. I remember what I wanted to say. One of the theories was that over that period of time, with all the cosmic rays and so on going through the probe, it might have gone through whatever frequency reference they were using on board.
Scrambled.
And well, not necessarily send it off into the weeds, but just moved a little bit. That was one theory.
Yeah.
It ended up being something else. I'll tell you what about that in a second. But then we commanded telemetry to be enabled on B via a command sent to A. So it was completely configurable and can address one and have it talk to my subsystem on board.
Boot back up.
Yeah, exactly, right. So this is when we turn them both on, and you can see them both running there in real time, coming down on the two receivers. So yeah, we just had the two radios there. And then, so this was a simple Flowgraph to get initial analysis of the telemetry going. Telemetry can be configured to run at different rates. And in this case, due to double shift and so on, it dropped in a PLL block, and that would track the carrier. And then it would bring it back down to baseband. You can see all the different versions now. It's perfectly centered on baseband. And then you can run it through this scope, and you can see these distinct clouds of points, which are the two ends of that phase modulation, your ones and zero. If you then get the argument, you can see very distinct transitions between negative and 1, 1. So that's exactly what you want to see on a nice strong signal. And then you can do this thing called cyclization or analysis, where you multiply the signal by a delayed version of itself. It's this little DSP trick you can do. And then you take the FFT of that. And once you do that, you actually get these peaks that indicate to you the periodicity of the component in the signal. So if you have a digital signal that's running at a particular rate, you will see the first strongest peak come up as the baud rate, or the symbol rate in your stream. And because the telemetry downlink can be configured to run a variety of different rates, we can use this trick to figure out the rate at which it was coming down. We would actually command it to run at a particular rate, but this was a way of confirming that that rate had been realized by the system. And then once you take that raw data, you run it through clock recovery, and then you can see that it's coming out with nice transitions. And then we knew what the frame format coming down was, and so we had there's this little filter there, and the matched response of the filter was actually the preamble of the frame, the synchronization codes in that frame. So we get this nice peak when it hits that synchronization before the next frame of data starts. And then there's another mode where it runs at a slow rate, and then has a different sort of thing. I'll sort of skip that. Essentially the same sort of thing. Phil Kahn is quite a legend in this sort of space probe decoding, and he wrote this convolutional decoder, and he claims the world's record for the largest Viterbi decoder for k equals 24. And so we used that as well later on to decode the telemetry when it was a bit weaker and you needed that extra computational gain. So some very initial decoding of the telemetry indicated that things were pretty good, and some tweaking and analysis of the trajectory based upon our pointing at Arecibo led to this sort of alternative orbit and reassessing of when it would do the flyby. And now our time had ended at Arecibo, but we still need to run our operations and be able to command it remotely. So we came back to California, but we had left the equipment there, so we had the ability to SSH in from California and control all this, and essentially, sit in the office and try and talk to the space probe, which is pretty neat. And I don't mention it here, but I was at DEF CON, and we needed to reboot one of the science instruments, and I got this message when I was watching one of the talks. I didn't want to lose my seat, because there's a lot of people there, and I've been queuing up for some time. And you don't want to get on the Wi-Fi at these conferences, because then you get hacked like that. Because it's a hacker conference. So what can you do? I didn't have any cell phone reception, because I picked the wrong carrier. But the guy next to me was visiting from Norway, and he had picked a carrier that had some bars, and he was nice enough to let me tether to his phone. So I ended up rebooting the science experiments on a space probe flying by the moon while sitting in the audience at DEF CON watching one of the talks. I have to...
Sure it wasn't a hacked hotspot as well.
Well, I was hoping, he seemed alright. I had a bit of a chat to him to suss him out first. Free station. So all in all, it worked out.
Yeah.
So that's back at the office. And it was cool because, this is no longer a high bandwidth link back to Arecibo, but you can run this ASCII art FFT. So that's actually the telemetry from the probe represented in an SSH terminal. So we wanted to look at the coherent and ranging modes and enable that in the probe, because that would enable us to exactly identify where in space it was and how far away it was. This was sort of this basic stuff built into that space probe, and we wanted to try and work with that. The downlink carrier can be put into this tracking mode where it'll track the uplink with a particular ratio, and in ranging mode, the downlink carrier will actually be modulated with whatever you send up. So NASA would customarily send up various pseudo-random tones and various other things, and then watch what they would look like when they would come back, and then be able to determine from that how far away the probe would be. Really clever stuff. And so here, this is actually looking at the signal coming back down, and as we would send the commands, this is the nominal frequency at which it's sort of idling at, and then when it would pick up our signal, it would jump out here in this coherent mode, because it's tracking our offset carrier, and then we would try and step it. And remember how I was saying we'd shift through the frequencies? That's what's happening here. So it's actually tracking our carrier, and then once it loses lock, you can see here it goes all fuzzy, and then snaps back. And so we sort of did some preliminary analysis on this. Remember I was talking about the initial setup wasn't really designed for proper, consistent transmission. That's when the master bus came in. So the original setup was we had the transmitter, we would send commands out, it would modulate the command, send it out, and then it was done. That was it. That's not actually how to do it properly. And the way the DSN does it, is the Deep Space Network does it, is the proper way. And that's where you send a constant carrier the entire time. It doesn't even need to be modulated. It's just something for the space probe to pick up and lock onto. But it's got to be there all the time. And then when you want to send commands, you modulate those commands onto the carrier. Or you put your pseudo-random codes onto the carrier to do your ranging. And once we did that, everything started working phenomenally. We had really great success in communicating with the probe, sending commands, and it would happen, and process them all the time. And so it felt like it should, as if NASA would have been doing it properly as well. So here is an example where, in fact, it locks on, and then in the radio I wrote another block to do this sort of sweeping stuff, and then I told it to sweep it a particular way, and what do you know? The downlink perfectly tracked it up to a point, and then I think I changed the frequency back and it snapped back again. So this is what we would have expected to see. And then I wrote this other computer radio program that would generate tones and have major, minor ranging tones in the way that NASA had done. Unfortunately, we never really got to use this, but it would have been cool because you could also send out a pseudo noise code out there and then wait for it to come back and do the correlations and actually, come up with a rough estimate of how far the probe was. And then what was cool is DSN actually did some ranging for us, and we managed to get dish time while they were doing the ranging. So we would listen on the same frequency on the downlink while they were doing their tones. And I can't quite see it here, but you can actually see their various ranging tones changing as they're doing their ranging. So it was nice to snoop on their process. So you can't quite see it here. So we had the telemetry happening, it was time now to decode it. So the first step was, once we had the framing, to actually get the raw data out, which is here. It comes out in these frames, and each of these frames, depending upon the frame count, would dictate which of these bytes will then fill out these things called subcoms. So subcoms were sort of other frames, and they would slowly be built up over time until you had enough data to actually decode what was going on. So those German hams that I was talking about are the guys out at Amsterdam, and they were a great help because when we were transmitting from Arecibo, they were listening on the other side of the planet, and so we had live telemetry coming back from them, and Arecibo could stay transmitting the entire time. And so, can we get a bit of volume? So this is what the telemetry sounds like at the 16 bit per second mode. It's a very low rate, and you would do that obviously when you'd be very, very far away from the Earth. And so if you go through the different steps here, you can see that doing the cyclization analysis there. This is another clock recovery, and I'll show you more in a minute. So that's 16. You go to 64. You're going to hear it come up out of the noise as the dish tracks in. You can hear, obviously, it's faster now. And then, if you switch then to the Telemetry Parser, this is a program that I wrote in Python. When it picks up the sync, you can see that it starts populating the frame. And as it populates the frame, it builds up the data, and then those bytes get taken out, and you've got analog subcom 2, analog subcom 1, and digital subcom. And these all relate to different elements of the telemetry, like temperature and pressure and frame counters. And in this screen, you can see that as it gets enough data, it begins populating all the telemetry elements. So you've got all the information about the propulsion system, the other redundant propulsion system, the spin rate, and all sorts of other interesting things there. So then at 512, which is mostly what we worked at, you can hear that it's higher. Now, I've heard this so many times, I don't know whether you'll be able to hear this, and maybe you guys and will be able to make out the repetition. But I'm going to indicate with my arm when the frame resets. You can hear it, it's the same sequence of tones. And you can see when it happens, this is when that match filter will tick over when you hit that point. And so finally, then you can go at the blistering rate of 2K. And then you can see in a moment when we hit the telemetry parser, it will update much quicker. So here you can read off that it's at 2K, doing the clock recovery, and you can see now that when we trigger on that frame sync, it happens much more frequently. So in here, it's always the same, and then beyond that, it's actually the data from the previous frame and data from the next frame. But it's a fixed sequence of this portion, so you can see that it's updating much more rapidly.
So this is after you've told the spacecraft up to speed?
Yeah, right. Yeah. And this is important too because when we were in science mode, we wanted to get more data down. And remember that the space probe is really simple. It doesn't have any onboard memory. So everything has to come down in real time, even the data in real time. Yeah. And so things we were interested in, so this is all the, for example, the log data from the temperatures from the various fuel tanks in the propulsion
So the
system.
memory is all hardwired, is it?
Yes. So this was, as I was saying, the analog subcom 1, analog subcom 2, and the digital subcom. And then, this is sort of our setup in mission control. We'd have a big screen there, and then we had a flight ops plan. When we were trying to do the maneuvers, it would dictate all the steps, and then we would confirm what we would hope to see on the telemetry radar. So these are members of the team there. Yeah, and this was actually the old McDonald's on the Moffett Field Air Force Base in Silicon Valley. And they had moved in there. It was just this eerie feeling because it felt like a fast food joint, but it was overrun with all this incredible space stuff. And so in addition to having the raw data come out, there's also a little app that I wrote to actually graph the stuff in real time. And this was quite helpful for temperatures and accelerometer and so on. So the probe would actually report back the signal strength that we'd hear from the Earth. So when the master blaster would be running, we would sort of have this there. And then in addition, we were looking at the accelerometer in particular. There's an accelerometer on board, and so every time you fire a thruster, you hope to see this impulse. and we had particular configurations where you fire a particular thruster a certain amount of times. Remember, it's a spinning probe, so every time it would come around, you would fire the thruster to try and move it. Unfortunately, we only really got one little burst, and then it would flatline after that. So things weren't going as we had planned, unfortunately. Every time we tried, remember there are 2 redundant systems, multiple different valves, and so on. And every time we tried to do it, we might get something at the very beginning, but then after that, we just get nothing. And the thing is, the very first time we tried any sort of firing was to spin the spacecraft up back again to its nominal spin rate. It had slowed down a little bit over time. And we did that, and it actually worked. We had it successfully fire, and the spin rate that was being reported back from the probe through the telemetry indicated an increase. So I thought, wow, this is great, everything's actually working. There's still fuel on board, the propulsion system working great. But what it had turned out is there had been some residual pressure in the line, and that's what had forced the hydrazine out on that initial attempt. And after that, there was no more thrust, and we couldn't explain why. The fuel had been logged, the fuel consumption during the initial mission had been logged, and so by all indications on paper, there was still plenty of fuel on board. And actually, remember how I showed you the temperatures? Those temperatures would also indicate to the thermal mass that you would expect of a tank filled with fuel, that there was still something in the tanks. So this is what the hydrazine propulsion system actually looks like. You've got your 2 redundant sets of tanks, you've got your different valves there, and you've got all your different thrusters. And we tried all sorts of different combination of things to try to get some movement out of the thing. Unfortunately, it didn't work. And so the theory is that although there was fuel on board, you actually have nitrogen pressure in there to push the fuel out of the tanks down to the thrusters. And over that period of time, there might have been an incredibly small leak, and it might have just
30-year-old craft, so.
Yeah. Stands to reason that it's certainly possible.
So is hydrazine hypergolic?
Pardon?
Is hydrazine hypergolic? Does it ignite just as it comes out, or do you have to ignite it?
It hits a catalyst bed.
Okay.
And so we turn the cat bed heaters on before we do the maneuvers, and as it hits that, then it actually produces the. But it's nasty stuff, so don't handle it, otherwise you'll die. Simply put. So we went out back into this orbit, and depending upon the sort of frame, it did the lunar flyby as was originally intended and has gone back out there. And we actually had turned some science instruments on, so we got some science data back, which is really neat. But unfortunately, it sort of went a little bit out of the plane of the solar system, out of the ecliptic that we had thought. Didn't quite get the amount of sun because remember the batteries had long died. It was absorbed power purely off the solar panels. And it went into an undervoltage state and it rebooted itself. And unfortunately, the transponders are on the non-essential bus. So the transponders rebooted and their boot up state is receive only. So we lost not only the telemetry, but we also lost the carrier, which meant that basically now it's impossible to find. We had another dish out there tracking for us and receiving some of the data at Moorhead State University. And it was neat because, remember how I was talking about the GPSDO? They had one of our USET with the GPSDO in there, and so I logged in remotely and then ran a little program to extract the coordinates where the USET thought it was. I'll punch those coordinates into Google Earth and then what do you get? That's easy. So yeah, this is some of their stuff from there. So that's the team there. We've got Austin, Jacob, Cameron, Dennis, Marco, that weird Australian dude. So as I say, Google came along and documented for us. If you're interested, you can check out the website. It's called spacecraftforall.com. Lots of pretty graphics and video. As you can see here, WebGL, that's the address. The idea was to keep in contact with the spacecraft for longer and then actually get the live telemetry coming down. So another part of this site was actually sort of a pretty visualization of the data feed, but unfortunately that didn't quite work out. So that's the team outside of the old McDonalds there, which is called MegaMoons. And behind us, you can't quite see that, there's a pirate flag sitting there. So yeah, that's pretty much that. I don't know whether you want to take. Maybe later you can grab these links. But oops, anybody recognize that scene?
Yeah.
This is what we wanted to avoid. That was the end of GoldenEye. So that's the mission. Any questions about the mission?
So how did you get the manuals from NASA? Right, like
I wasn't really part of that. They had sort of done that by the time we joined.
Yeah.
But actually, a couple of the guys have former employees or have very strong connections.
Right.
And you know the market.
Figure out all the decoding.
Yeah.
And who wrote the telemetry or the instructions on how you're going to reposition this thing? Who was coming up with all that?
So Marco, who you saw before, he was the guy in charge of the sort of orbital ops maneuvers, and he had some crazy MATLAB code, I think, to process all that. Cameron was the flight director, so he came up with the flight directions for each day and all the steps he would go through to do it. And that included having those commands pre-prepared to configure the thrusters and then fire them and do it all together. Yeah. So they had sort of pre-computed all that.
And its current orders will it ever come back?
Oh yeah, it'll come back, it'll keep doing its thing as it's been doing since.
So is there any chance of getting it to...
Well, since the transponders can't hear it, and so it'll be
You won't be able to track it.
practically impossible to figure out where it is and it's going. I mean, you could take a pot shot and especially if the DSM gave us more time, they had incredibly powerful transmitters, like ridiculously powerful, far beyond what we could do at Arecibo. So you could, and that might have been with as well. So you just blast it out there and see where you might be able to
turn it back on.
Yeah. But the likelihood of that is pretty slim.
Because it's not interesting enough for it.
On to the next thing.
Yeah. We sort of know it's got no thrusters now, so you could turn it on, listen to the science, but yeah.
Well, I mean, from the science point of view, it's interesting because there are, a few probes up there doing science, but consider they're only a very small handful. So if you have another probe that's positioned slightly elsewhere in the solar system, it can still provide you very valuable data. And I think one of the stereo satellite space probes is no longer functioning. Does anybody know about that? The stereo A and B? One of them's offline now.
Yeah.
So, I mean, there's
More
an
data's
argument.
always good, yeah.
Yeah. So if you've got something up there, make the best.
Absolutely. Yeah.
Any other questions?
Did this make anyone nervous? Did you get any visits from anyone? Did anyone sort of concerned that some guy? Oh no, was anyone concerned, like from NASA or from anyone else, like, hey, these guys are about to take over a satellite?
I think there was good dialogue, good communication channels back and forth, and everything was sort of being handled above board.
It was the first time NASA let anyone control anything.
Yeah, that's the part that surprised them.
It was supposed to be setting that sort of precedent where they could actually offload responsibilities to the sort of private.
Great idea.
Yeah, that was awesome.
Science centers. So that was that Space Act.
Who was funding it? Other than just that crowdsourcing?
Just a crowdsourcing.